Let us start molecular orbital continuation. In the molecular orbital theory, molecular orbital energy levels we will see. Now we will take a energy levels of orbitals in the atom. Now we will take it is 1s orbital energy, 1s orbital energy. It is 2s orbital energy. This is a 2px, 2py, 2pz orbitals energy. It is for one atom. It is for one atom atomic orbitals energy we have given. Now we will see another atom atomic orbitals energy we will give. Another atom. This atom and this atom may be same kind or different kind. Okay. Sorry. So now we will consider that 1s, that 2s, that is having three orbitals, 2px, 2py, 2pz. Three orbitals we have given. They are undergoing a linear combination. Therefore, due to linear combination, this will give sigma 1s, sigma 1s, then sigma star 1s, sigma star 1s, then it will give sigma 2s, then sigma star 2s, sigma star 2s, then it will give sigma 2pz, then it will give pi 2px is equal to pi 2py, then pi star 2px, comma pi star 2py, then sigma star 2pz, sigma star 2pz. This is the energy level of molecular orbitals. Molecular orbitals energy level is like this. Molecular orbitals energy level is like this is there. Okay. This is the energy level of molecular orbitals. Okay. How this energy level is there in the sense sigma 1s less than sigma star 1s less than sigma 2s less than sigma star 2s less than sigma 2pz less than pi 2px equal to pi 2py is less than pi star 2px is equal to pi star 2py less than sigma star 2pz. This is for which case in the sense for O2 molecule, F2 molecule, it is possible. For O2 molecule, F2 molecule, it is possible. This is the order of energy, energy of molecular orbitals for O2, F2. Sorry. What about for N2? What about for nitrogen, N2, C2, B2, Be2, Li2, H2, He2 for this? How it will be there? That point we'll see. Okay. Now, for N2, how the energy of atomic orbitals will be there? Then we'll see energy of molecular orbitals. So, for H2, He2, Li2, Be2, B2, C2, N2. For these cases, what happens means 2s atomic orbital, 2s atomic orbital interacts with 2p atomic orbitals. 2p atomic orbitals. Interaction is possible. For these cases, that means hydrogen to nitrogen, 2s atomic orbital interacts with the 2p atomic orbital. Why not for O2 and F2? For O2 and F2 also interaction is possible. But due to this interaction, some changes taking place in these cases, but changes due to interaction, change is not there. Due to interaction, change is not there in this order. In this order of energy of molecular orbitals, change is not there for O2 and F2. But in this case, this order is having some change. Sir. Now, due to this interaction, what will happen? Interaction means what? energy exchange. Okay, interaction means, this interaction means energy exchange, that's all. Energy exchange. Energy exchange means what? One is losing energy, another one is gaining energy. That is the meaning. So here 2s atomic orbital and 2p atomic orbitals undergoing interaction, in the sense one will lose energy, one will gain energy. So which will lose and which will gain? That means one which has higher energy will lose, one which has lower energy will gain, isn't it? So which is having lower energy? 2s. Which is having higher energy? 2p. So which will lose? 2p. Which will gain? 2s. It is general. Okay. But here, which is losing energy means 2s atomic orbital is losing, 2p atomic orbital is gaining. Okay. So in exception manner it is there. In exception manner it is there. 2s atomic orbital, 2s atomic orbital loses energy, while 2p atomic orbital, 2p atomic orbital gains energy, Okay. 2s atomic orbital is losing, while 2p atomic orbital is gaining. So 2p atomic orbital means 3 atomic orbitals possible, 2px, 2py, 2pz, which will gain energy, whether all 3 or any one. For that case, which is interacting, that will gain energy. In this 2p in the sense xyz is there. Among them, which is interacting with the 2s, that will gain energy. Which is not interacting, that will not gain energy. Okay. Sir, that is of course correct. So which will interact, whether all 3 or any one, that we will see. For which we will take internuclear axis is z axis, we will take internuclear axis, z axis we have taken. Now we will consider 2s atomic orbital. It is what, in the sense 2s atomic orbital. Now we will consider it is 2pz atomic orbital. It is 2py atomic orbital. Next 2px atomic orbital. Okay, these 3 atomic orbitals are perpendicular to each other. So how the interaction is there? Now see, this 2s and 2pz are along the internuclear axis. Along the internuclear axis, if you see 2s and 2pz, therefore 2s interacts with 2p. 2s interacts with 2pz, because internuclear axis is z axis. So 2s can interact with 2pz but not with 2py or 2px. 2s can interact at a time with one 2p orbital, not with all the 3 2p orbitals. That one 2p orbital, which in the sense what is the internuclear axis, that internuclear axis z means 2pz atomic orbital will interact with 2s. So 2s is interacting with the 2pz atomic orbital, but not with the 2px or 2py. Okay. Therefore, what happens to the energy? What happens to the energy if you see energy of 2s? Energy of 2s decreases, energy of 2pz increases, whereas energy of 2px, 2py remains same. Energy of 2s getting reduced, 2pz getting raised, 2px, 2py remains same. Why 2px, 2py remains same? Because they are not interacting with the 2s. 2pz interacting, that's why its energy rises. So due to this interaction, what happens to the molecular orbitals energy level, that we will see. Now we will take Now we'll take atomic orbitals. Atomic orbitals 1s, atomic orbitals energy 1s, here 2s, here we'll say 2px, 2py, 2pz. This 1s atomic orbital on linear combination gives sigma 1s and sigma star 1s. Okay, with another 1s atomic orbital. Okay, now this 2s atomic orbital on linear combination gives sigma 2s and sigma star 2s, sigma star 2s. Then this 2p atomic orbitals on linear combination gives sigma 2pz. Then pi 2px is equal to pi 2py. Then pi star 2px is equal to pi star 2py. Then what means sigma star 2pz, sigma star 2pz. This is the order of energy general. Now because of interaction due to this, okay, because of this, what will happen? What will happen to the energy? Now regarding this oneness remains same. This 2s, the 2s energy getting reduced, 2s energy getting reduced to atomic orbital, I am saying. Okay, then regarding this 2p, regarding this 2p, what happens means 2px is equal to 2py remains same, but 2pz raised, 2pz energy raised. Okay, so 1s atomic orbital remains same, 2s atomic orbital getting reduced, 2px 2py remains same, 2pz atomic orbital getting raised. Like this is there. Okay, now we will go for what in the sense linear combination. So this oneness on linear combination gives what in the sense sigma oneness, same like this. Here how it is there, like this only sigma oneness will be there, sigma oneness. Here how sigma star oneness is there, in the same manner sigma star oneness will be there. Okay, sigma 2s is here, sigma 2s is here. Okay, now sigma 2s will be where now, in the sense it will be down, it will be down now. Why? Because 2s energy getting reduced. Then sigma star 2s is here, sigma star 2s is here, that energy also getting reduced, that energy also getting reduced. Okay, but sigma star 2s energy will be greater than sigma 2s. Okay, regarding pi 2px and pi 2py, pi 2px and pi 2py energy will remain same, there is no change, there is no change. But this sigma 2pz, this sigma 2pz is the no, that sigma 2pz energy will become greater than this pi 2px and pi 2py. The sigma 2pz energy getting raised. Why? Because 2pz energy getting raised. Okay, then regarding this pi star, we will see regarding this pi star 2px and pi star 2py energy remains same, in that there is no change. Pi star 2px is equal to pi star 2py. Then we will see regarding sigma star 2pz. Regarding this sigma star 2pz, this energy getting raised, this energy getting raised. Okay, because of this interaction, 2s 2pz is interacting, because of that molecular orbitals energy is like this when compared to this. So now we will see the order, how the order is there means, now least energy if we see sigma 1s, least energy sigma 1s, next higher energy sigma star 1s, next higher energy sigma 2s, next sigma star 2s, next higher energy if we see what is there, pi 2px is equal to pi 2py. Okay, next higher energy is sigma 2pz, next pi star, next sigma star, like this is there. Okay, it is the order of energy of molecular orbitals for which case means up to n2, up to n2. Therefore up to n2, how it will be there, from h2 to n2, from h2 to n2, how it will be there, means sigma 1s energy less than sigma star 1s less than sigma 2s less than sigma star 2s less than pi to px is equal to pi to py, then less than sigma to pz less than pi star to px is equal to pi star to py, then less than sigma star to pz, sigma star to pz, like this will be there. Okay, so from hydrogen to nitrogen, like this is there. But if you take O2 and F2, O2 and F2, if you take sigma to pz comes here, sigma to pz comes here, for which case in the sense for O2 F2, so and so. Okay, now we will see electronic configuration, molecular orbital electronic configuration. We'll see how to fill electrons in molecular orbitals, for which rule you have to follow in the sense of the principle, Hund's rule, Pauli's exclusion principle we have to follow. Okay, now we will take the species H2 plus. H2 plus in the sense it is hydrogen atom plus H plus, that is called H2 plus. Hydrogen atom is having 1 electron, H plus is having 0 electrons, so therefore totally 1 electron. This 1 electron goes to which orbital in the sense least energy orbital, which is the least energy means sigma 1s. To this 1 electron goes to sigma 1s orbital, therefore H2 plus is having electronic configuration sigma 1s 1. Now, this 1 electron present in bonding molecular orbital, therefore it is responsible for bonding. Sir, now this 1 electron is responsible for bonding. Okay, now we will see what is the bond order. What is the bond order? We will see. Okay, bond order in the sense it tells about number of bonds between two atoms in a molecule. Okay, between two atoms in a molecule. That's what this bond order says. Now, here 1 electron is responsible for bonding. Generally, one bond in the sense two electrons will be there. Two electrons responsible for one bond. Covalent bond means normal covalent bond means two electrons responsible for one normal covalent bond. Here one electron is responsible, therefore it is representing half bond. Therefore, bond order is how much means 1 by 2. Bond order is 1 by 2 of bond, we can say. Next we will take a H2 molecule. Will take H2 molecule contains two hydrogen atoms. Each hydrogen atom is having 1 electron, therefore totally 2 electrons. These 2 electrons goes to sigma 1s. Sigma 1s is one orbital, one molecular orbital. It can take maximum 2 electrons, so we will give 2 electrons here. So electronic configuration for H2 molecule is sigma 1s2. Now we will see the bond order. Bond order is equal to 1 because 2 electrons responsible for normal covalent bonding. Therefore, bond order is how much in the sense 1, we can say. Okay, next species we will take He2 plus. We will take He2 plus in the sense He plus He plus. Okay, this helium atomic number is 2, therefore 2 electrons. He plus means atomic number 2, but plus 1 means 1 electron is lost, therefore only 1 electron will be there. Totally 3 electrons. Now we will write molecular orbital electronic configuration. Least energy molecular orbital is which one in the sense sigma 1s. Next higher energy level, which one in the sense sigma star 1s. Now here 3 electrons are there. First 3 electrons we will take here. Now sigma 1s in the sense one molecular orbital. One orbital can take maximum 2 electrons. Therefore give 2 electrons here. Remaining 1 electron give to sigma star 1s. Set. Now here sigma 1s2. Sigma 1s2 means these 2 electrons are responsible for bonding, but this electron is responsible for anti-bonding. Anti-bonding in the sense this electron is affecting this electron. This electron is affecting this electron because it is responsible for anti-bonding. No, it is responsible for anti-bonding in the sense what happens to the net effect? It is responsible for bonding. It is responsible for anti-bonding means it is affecting the bonding. That is the meaning. No, therefore it is forming. This forms full bond. This forms full bond. Full bond in the sense one normal covalent bond. Okay, full bond in the sense one normal covalent bond, we can say one normal covalent bond. What it does, it is affecting this, affecting this bond. In what way? Because of this one off bond is affected, off bond is affected, off bond is affected, we can say, because of this electron here off bond is affected. Therefore what is the net? Net says that remaining off bond is there, remaining off bond is there, we can say remaining off bond is there. Actually these two electrons forming full bond, one normal covalent bond. This electron, what it does, it is affecting this electron, it is affecting this bond. This has affected how much bond, means half bond. So how much is remaining? Half bond only is remaining. So half bond is remaining means bond order is equal to 1 by 2. So how to find bond order? In the sense we will write number of electrons due to bonding molecular orbitals minus number of electrons due to anti-bonding molecular orbital by 2. Now we will substitute. Bonding molecular orbital contains 2 electrons. Anti-bonding molecular orbital contains 1 electron by 2 is equal to 1 by how much, means 1 by 2. So bond order is how much, means 1 by 2, we can say. Okay, so anti-bonding molecular orbital contains electron means that will affect bonding molecular orbital electron. Okay, so He2 plus is having bond order how much, means 1 by 2. Therefore in He2 plus species how much is there, means 0.5 is the bond order. Sir, now next we will take He2, we will take He2. He2 contains sum of helium, 2 helium atoms. This atomic number 2, therefore it is having 2 electrons. Totally how much, means 4 electrons is there. Now we will write sigma 1s2, sigma star 1s2. Now this sigma 1s2, it forms a full bond, it forms full bond, it forms full bond. Now what it does means it will affect that full bond, affect that full bond, affect that full bond. Therefore what is the net? Net says no bond, net says no bond, because it is forming full bond, it is going and affecting this full bond. What is the net? Nothing, no bond. In the sense what is the bond order? Bond order is 0. Sir, we will calculate bond order as per the formula. Now bond order is equal to number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding molecular orbital by 2 is equal to how much? 0. Therefore bond order is 0. Bond order is 0 means what is the meaning? No bond. No bond is there means this, is it a molecule? Will it exist or not? Not existing. So we can say this molecule is not existing. Okay, now you say that why do we say noble gases are monoatomic molecules? Have you got idea? Noble gases are monoatomic molecules. Noble gases, we can say monoatomic molecules. Atomicity is 1. Noble gases do not exist as diatomic molecules. Why it is not existing as diatomic molecules? Because there is no bond. No bond in the sense not existing. So diatomic species is not possible. So the noble gases do not exist as diatomic molecules, only exist as monoatomic molecules. So atomicity is 1 for noble gases. Sir, next we will take Li2. Li2 we will take. Li2 contains 2 lithium atoms. Atomic number of lithium is 3, therefore 6 electrons are there. So we will write sigma 1s2, then sigma star 1s2. After sigma star 1s, what is there? Means sigma 2s is there. So remaining electrons will distribute here. Okay, now we can say that this forms full bond. This will affect this bond completely. So it is forming bond, that bond is completely affected by this. Okay, therefore these two cancel with each other. Okay, these two cancel with each other. What is the result? Means this one, this is forming full bond, therefore bond order is how much? In the sense 1. Okay, as per formula we will calculate number of electrons in bonding molecular orbitals here 2 minus number of electrons in anti-bonding molecular orbital, that is 2 here by 2. Therefore it is equal to how much? In the sense 1. Bond order is how much? In the sense 1, we can say. So we said bond order is 1 for this. Okay. Next, Next we will see here this 2s contains sigma 2s contains 2 electrons. 2 electrons in the sense unpaired electrons not present. Unpaired electrons not present. Unpaired electrons not present means we have to say diamagnetic species. Diamagnetic species. Unpaired electrons present means we have to say paramagnetic species. So paramagnetism in the sense unpaired electrons present. Diamagnetism in the sense unpaired electrons not present. Like that we have to say. Okay. Next we will take another molecule, that is a Be2. Be2 contains two beryllium atoms. Beryllium atomic number is 4. Therefore, total number of electrons 8. Electronic configuration sigma 1s2, sigma star 1s2, sigma 2s2. After sigma 2s, what is there means sigma star 2s is there. So we will write electrons. In this case, you see that this sigma star 1s affect completely sigma 1s. Sigma star 1s cancel the effect of sigma 1s. Sigma star 2s cancel the effect of sigma 2s. Each and everything cancel with each other. Therefore, what is a net? Net is nothing. Net says that no electron is responsible for bonding. Therefore, bond order is how much means 0. We will see as per the formula. Number of electrons in bonding molecular orbitals means 4. Number of electrons in anti-bonding molecular orbitals means 4 by 2 is equal to how much means 0. Bond order is 0 means this species does not exist. This Be2 is not existing. Okay, so Be2 does not exist. Like this you can say. Okay, next species you will see B2. B2 in the sense atomic number of boron is 5. Therefore, 10 electrons. 10 electrons in the sense sigma 1s, then sigma star 1s, then sigma 2s, then sigma star 2s, then what will come after sigma star 2s? What is there means understand that pi 2px comes. Pi 2px is equal to pi 2py. Okay, now these two molecular orbitals are having same energy. Therefore, you have to fill the electrons in these two molecular orbitals as per Hund's rule. As per Hund's rule in the sense half filled first, then only pairing. Okay, half filled first, then only pairing. Okay, so totally 10 electrons are there. How many distributed in the sense 2, 4, 6, 8? 8 distributed. Remaining how much? 2. How to distribute 2 electrons here? Okay, how to now 2 electrons are there. How to distribute 2 electrons here? As per Hund's rule. Why? Because these two are degenerate orbitals. Why they are degenerate? Because their energies are same. Therefore, the 2 electrons distribute 1 here, 1 here. Like this you have to distribute. Okay, now we will see the bond order. Now sigma star 1s will cancel sigma 1s. Sigma star 2s will cancel sigma 2s. So what is which is alone responsible? These two electrons. These two electrons present in bonding molecular orbital. Therefore, these two electrons are responsible for bonding. Here, two electrons are responsible for bonding. Therefore, one bond will be there. That means one bond in the sense in B2 single bond is present. In B2, what bond is present means single bond is present. Single bond means generally we will say sigma bond, isn't it? Single bond means we will say generally sigma bond. Double bond means 1 sigma 1 pi. Triple bond means 1 sigma and 2 pi will say. Now you say this is single bond. This single bond is sigma or pi. What shall we say? Now you see this here, which is responsible for bonding? Pi 2px and pi 2py. That means pi molecular orbital is responsible for bonding. Pi molecular orbital will form which bond? Pi bond. Therefore, this bond is which bond? Pi bond we have to say. Have we got an idea? Here pi bond exception. Understand that generally single bond means sigma bond. But here it is not single bond. What bond it is? Pi bond we have to say. Okay. Therefore, in B2 species, pi bond is present. Therefore, this B2 species exists in vapor state. Okay. Next we will take C2 will take. C2 contains 12 electrons. 12 electrons in the sense sigma 1s, sigma star 1s, 1s, sigma 2s, then sigma star 2s, then pi 2px is equal to pi 2py. Now, how to fill electrons here you see? How to fill electrons here you see? Here 8 electrons over, remaining 4 electrons are there. First electron here, second electron here, third electron here, fourth electron here. Okay, like this we have to fill. Now we will see the bond order. Now sigma star 1s cancel sigma 1s, sigma star 2s cancel sigma 2s. Now this is forming 1 pi bond, this is forming 1 pi bond, therefore bond order is equal to 2. Now we will see in C2 species double bond is there, bond order is 2, therefore double bond is there. Generally double bond means 1 sigma and 1 pi, but in this case both bonds are pi bonds, both bonds are pi bonds. Why? Because it is responsible for bonding 1 pi bond, it is responsible for bonding 1 pi bond, therefore 2 pi bonds are possible. Here 2 pi bonds are possible. So C2 species contains double bond, both bonds are pi bonds, therefore C2 species exist only in a vapor state. Okay, next we will take a N2 species we will take. Now we are taking N2. N2 contains 14 electrons. Now sigma 1s, sigma star 1s, then sigma 2s, then sigma star 2s, then pi 2px, pi 2px, pi 2py, then sigma 2pz, sigma 2pz. Okay, sigma 2pz we can say. So n2 contains 14 electrons. That 14 electrons we can write like this, we can write. Okay, so we have written like this. What is the bond order, that we will see. Now we have to see the bond order. Sigma 1s, sigma star 1s cancel, sigma 2s, sigma 2 star 2s cancel. Now it is responsible for 1 pi bond, it is responsible for 1 pi bond, it is responsible for 1 sigma bond. Therefore in N2 species what is there in the sense 1 sigma bond is there and 2 pi bonds are there. Okay, nitrogen bond order is 3 triple bond, 1 sigma and 2 pi bonds in the case of N2. Now we will take N2 plus, we will take N2 plus in the sense remove 1 electron here, therefore becomes 13 electrons. From where we have to remove 1 electron? From sigma to pz you remove 1 electron, therefore what is the configuration in the sense sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px, pi 2px, then pi 2py, pi 2py, then sigma 2pz, sigma 2pz. Okay, it is the electronic configuration of N2 plus. Now so the what is how the bond order will be there, we'll see. Sigma star 1s cancel sigma 1s, sigma star 2s cancel sigma 2s. Now it forms 1 pi bond, it forms a 1 pi bond, it forms a half sigma bond. Why? Because bond order here 1 electron is responsible for bonding, therefore here what is a bond order in the sense 2.5, here what is a bond order in the sense 3. Sir, what is the bond length, that we will see. Here how the bond length will be there, here how the bond length will be there, that point we will see. Here more, here 6 electrons responsible for bonding totally, here 5 electrons responsible for bonding. 6 electrons responsible means more attraction, more attraction means atoms will be closer, therefore bond length will be less. Here 5 electrons are responsible for bonding, that means less number of electrons responsible for bonding, that means less attraction, less attraction means atoms will be somewhat far away, therefore bond length will be high. So if bond order is high, bond length will be low, like this we can say. Sir, next species will take a, what is that means O2 will take, O2 contains 16 electrons, that will write a sigma 1s, sigma star 1s, then sigma 2s, then sigma star 2s, then what will come in the sense pi 2px, will it come or not, means no. But up to nitrogen what we discussed, up to nitrogen what we discussed, after sigma star 2s what we said, pi 2p we said, after pi 2p only sigma 2pz we said. But in the case of oxygen, in the case of oxygen after sigma star 2s what will come in the sense pi will not come, what will come in sigma 2pz only comes. Sir, so then pi 2px, then pi 2py, pi 2py, then what will be there in the sense pi star will be there, pi star 2px is equal to pi star 2py. So up to that, up to this how many electrons we have filled, that will say here 2 4 6 8 10 12 14, 14 electrons we filled, but here how many electrons are there, 16. Now how to fill that remaining 2 electrons in the sense, as per Hund's rule, 1 electron you fill it. Here 1 electron in the sense unpaired electrons present in the O2 species. So unpaired electrons present in the sense this O2 is paramagnetic, this O2 is paramagnetic we can say. Okay, so in the O2, unpaired electrons present, therefore it is paramagnetic, we can say. So the paramagnetic nature of O2 is explained by Hund's rule, sorry, not Hund's rule, molecular orbital theory. Okay, this O2 is having paramagnetic nature, that is explained by molecular orbital theory. Okay, what about this paramagnetic nature by valency bond theory? Is valency bond theory explained paramagnetic nature of oxygen or not? That point we'll see. Okay, now valence bond theory will see. Now oxygen molecule will take. Oxygen molecule contains two oxygen atoms. In this here this valence shell contains 6 electrons. The 6 electrons like this. Here valence shell also 6 electrons. Now what is happening means these two electrons going for bonding. These two electrons also going for bonding. Okay, so as per valence bond theory, we have given like this. So now we will give two oxygen atoms separately. We will take. Okay, now oxygen atom helium configuration 2s2 2p4. 2s2 2p4 we will write. 2s we have given. 2p we will give. 2p contains 4 electrons. That 4 electrons we have given like this. Now another oxygen atom we will take. That another oxygen atom configuration is helium 2s2 2p4. That this is 2s2 we have given, and 2p4 we are giving here. So how the bonding takes place, that we will see. Now these two electrons going for bonding. When they are coming for bonding, the electrons will become what? Opposite spins. Okay, we have given parallel spins, but when they are going for overlapping, during that time electrons will become opposite spins. Therefore, this is opposite spins means it is paired up. These two electrons paired up. Similarly, these two electrons also going for bonding. Therefore, these two electrons also paired up. So paired up in the sense that now see, no unpaired, here pairing, here pairing, here pairing, here pairing. No unpaired electrons in this. So O2 is not having unpaired electrons as per valency bond theory. Experiment says O2 is having paramagnetic nature. So is valency bond theory explains paramagnetic nature of O2? No, sir. Now what molecular orbital theory says, that we'll see. As per molecular orbital theory, it is the electronic configuration. This electronic configuration contains unpaired electrons. Due to presence of unpaired electrons, it is paramagnetic. That is explained by molecular orbital theory. So paramagnetic nature of O2 is explained by molecular orbital theory, but not valency bond theory. Sir, okay. Now we'll see what is the bond order of O2. What is the bond order of O2, that we'll see. Sigma 1s, sigma star 1s cancel, sigma 2s, sigma star 2s cancel. Then sigma 2pz forms one sigma bond. Okay, one sigma bond is formed. Then pi 2px is having 2 electrons, pi star 2px is having 1 electron. So this 1 electron is cancelled by this. So remaining one will be there. It forms off bond. Pi 2py contains 2 electron, pi star 2py contains 1 electron. This 1 electron cancel this 1 electron. So remaining one will be 1 electron. That 1 electron will form off pi bond. Here off pi bond, here off pi bond. Totally one pi bond. One pi bond. Therefore, what is the bond order means? Bond order is 2. Okay, now we will see as per a formula we will calculate bond order. Okay, now we will take bonding molecular orbitals only. We will consider those electrons. We will calculate here 2, here 4, here 6, here 8, here 10. So bonding molecular orbitals giving 10 electrons. Now anti-bonding molecular orbital will see here 2, here 4, here 5, here 6. Therefore 6 by 2 is equal to how much in the sense 2. So bond order is 2. So for O2, what is the bond order in the sense 2 we can say, and it is paramagnetic due to presence of unpaired electrons present in pi star 2px and pi star 2py set. Next we will take O2 plus we will take. O2 plus means from O2 how many electrons we have to remove? 1 electron we have to remove. So remove 1 electron and see the electronic configuration for O2 plus. Now you say O2 plus is a paramagnetic or diamagnetic. What do you say? Sir, O2 plus is a, what do you say, paramagnetic or diamagnetic? Think and say. Next, what is the bond order of O2 plus when compared to O2? You think. Then how the bond length of O2 plus and O2 will be there? That also you think it. So compare bond order, bond length, then bond strength, then paramagnetic nature or diamagnetic nature, then which is